In the preceding clip, we saw how the matrix 2, 5, negative 2, 4 defines a system of differential equations. If we assume the solution y equals e to the lambda t x1, x2, we obtain the equation 2 minus lambda 5, etc., times x1, x2 equals 0, 0, with the condition that the determinant of that matrix be 0. This gives us three equations in three unknowns, lambda, x1, x2. We solve those equations. We get two different values for lambda, 3 plus 3i, 3 minus 3i. Plugging those values into these equations, we get solutions for x1, x2, giving us the eigenpairs, 3 plus 3i, 1, 1 plus 3i over 5, and I'm not going to read this one to you. You can see what it is, and we've already seen it, implying the solution set, e to the 3 plus 3i times the first eigenvector, e to the 3 minus 3i times the second eigenvector. Since the eigenvalues are distinct, our solution set is a fundamental set, so we have solved the original system of equations. We have a general solution, c1 times this plus c2 times this. And I'm not sure I pointed to the right thing, but c1 times this, c2 times this. Now, let's go ahead and apply Euler's identity to get the equivalent forms of these exponentials. So e to the 3 plus 3i equals e to the third times e to the 3i. And I've left something off of both of these. The assumed solution was, of course, e to the lambda t times the x1, x2, and I simply didn't write down the t's in these exponents, so I had to go back and repair that. I didn't discover that till I got down here and realized something was missing. So we got to put the t's in here. Now, e to the 3t is simply a function of t. E to the 3it, by the Euler identity, it's e to the 3t. Some days I can talk and write at the same time, some days apparently I can't. Okay, it's e to the 3t multiplied by, again applying the Euler identity to e to the 3it, that's going to be cosine of 3t plus I sine of 3t. So that this first solution is going to be e to the 3t multiplied by the cosine of 3t plus I sine of 3t multiplied by the vector 1, 1 plus 3i over 5. And of course this is going to distribute over these components of the vector, so that the first component is just going to be our e to the 3t times the cosine of 3t plus I sine of 3t and excuse that for being bunched up, but you can see that this simply goes through here, and then whatever this times this happens to be. So let's think about what we get if we multiply the cosine of 3t plus I sine of 3t by I plus 3i, 1 plus 3i over 5. Cosine of 3t plus I sine of 3t. Now I'm going to leave off the e to the t. I'm also going to leave off the division by 5 for right now and just look at the essential complex, the product of the complex numbers that are involved here, and then we can multiply the e to the 3t over 5 by the result. So that this is equal to what? It's cosine of 3t times 1 plus I sine of 3t times 3i. That's going to give us negative 3 times the sine of 3t. So we have cosine of 3t, write this out carefully, minus 3 sine of 3t. And this is the real part of our solution. And then the other two terms that we get when we use the distributive law to multiply these two expressions are going to be I sine of 3t times 1 and cosine of 3t times 3i. So that's going to be 3 cosine of 3t plus sine of 3t. So we have a real and an imaginary part. And I'm going to have to write kind of small to put this in here, but we'll write it a little bigger on the next page. So we're going to have e to the 3t multiplied by, first of all, cosine 3t minus 3 sine of 3t. And then it's going to be plus I times 3 cosine of 3t plus sine of 3t. Close the bracket. Now that's written way too small, and I don't expect you to be able to read that. I'll rewrite it on the top of the next page. Okay, rewritten, we have the same expression here. I forgot to put the division by 5 here, which makes this even worse. But again, simply multiplying this by this, the e to the 3 plus 3it is e to the t times cosine of 3t plus I sine of 3t. That simply distributes through and gives us this term for the first component, and in light of this multiplication here, we get this for the second component, where I've reintroduced the e to the 3t over 5 that comes from the e to the 3t here and the 5 in the denominator here. Now I'll write this down off camera, but we can see what happens next. We might not anticipate this, but we can separate this solution vector into a real and an imaginary part. The first component, the real part, will be e to the 3t cosine 3t, first component. Second component will be e to 3t over 5 times the cosine of 3t minus sine of 3t. And then we can write a separate vector for the imaginary component. So I'm going to go ahead and do that. We first see the real part. Ignoring the parts that have i's, we end up with this. And then it's going to be, and I'm not going to have room to write it over here without bunching it up, so I'm going to write plus I multiplied by the imaginary parts of these two components. And writing those components out, the sine of 3t here, the 3 cosine 3t plus sine of 3t here, along with our e to the 3t coefficient here and our e to the 3t over 5 coefficient here. And I noticed in writing this out that I neglected to put this much of the second component here in parentheses. And I've labeled this solution as the real part of this function, this as the imaginary part of this function. Now, a really important idea is the real part alone solves the original system of equations. So if I plug this real part into the system of equations that's represented by this matrix, I should get a solution if I've done everything right and kept all my constants straight. Furthermore, the imaginary part. Part alone solves the original system of equations. So, starting with the original system defined by this matrix, we obtain a fundamental set. We take the first vector in the fundamental set, and we haven't talked about the second, but it's treated in exactly the same way. We take the first vector in the fundamental set, and we expand it into its real and imaginary parts. We get this vector, we separate it into its real part, its imaginary part, and now we've claimed that the real part alone is a solution to the system, and so is the imaginary part alone. It's not difficult to prove this in general, but for the moment we're just going to verify it for the real part of this solution. We're going to plug this real part back into the original system of equations and verify that it is indeed a solution.